Hey guys, I wanted to go over something real quick before we start this video. When you see a bold real number system R, and if you notice there's going to be it looks like an exponent, um, but it's actually just a superscript. This is to let you know that you're in the real number system and that there will be two entries. For example, R squared indicates that we're talking about the set of all vectors with two entries, both of which are real numbers. If you happen to see a bold R3, that just indicates we're talking about a set of all vectors with three real number entries. And then later in the class, we're going to see R with a superscript n, and then you'll know that all vectors in the set have n real entries. And anyway, I just wanted to bring that up before we started this video and got it going. A little bit of definitions. A matrix with only one column is called a column vector. Vectors u and v are given here as examples. And here's the notation. U and v belong to R2. Two entries, both real numbers. Okay, now for matrices, if you're going to add or subtract, they have to have the exact same size. But then it's just a matter of adding or subtracting the same position. For example, u plus v, 0 plus -1 is -1. Bottom entries, 4 plus 2 is equal to 6. Scalar multiplication by some constant, for example, let u be the vector 1, 7, and we're going to have a scalar of 2. When you multiply, you just simply take your scalar times your vector, and you're going to multiply each entry by the same number. So 2 times 1, 2 times 7, that gives us a product or a scaled multiplication of 2 and 14. If we let u be the column vector 4, -3, and we let v be the column vector 1, 0, then you can find combinations of scalar multiplication and addition or subtraction. 2 times u plus 3 times v. Since u and v are the same size, the addition can be done. Size doesn't matter as far as scalar multiplication. So if we double u, that's going to be 8 and -6. And if we triple vector v, that's going to be 3 and 0. Take care of your scalar multiplication first, and then now we can add same positions. 8 plus 3 is 11. -6 plus 0 is -6. And remember, vector u is 3. Again, vectors u and v were in R2. U plus v is the fourth vertex of the parallelogram. Now, with the vector addition, if you think of this as the coordinate system that you're used to, the x-axis is your x1, and the y-axis is your x2. Vector u, if you were to plot, excuse me, this is just visual. If we take vector u, we'll do a visual down here with this one, and vector v, this is just to illustrate the parallelogram. If you were to pick up vector u and put its tail at the beginning, or excuse me, at the arrowhead of v, if you take this vector and keep it running in the same direction, you will land here at the sum of those two vectors. You could also take vector v, pick it up, have it run the same length and direction, and you'll land at the same spot here. So that's all that meant about the vector addition being the combination or result of u or v being added on to the other one. If you add v to u, or if you add u to v, you're going to land at the same spot. Okay, so here's how it would look visually. If we let vector u be 2, 2, and think of going to the point 2, 2, vector u, Vector V, negative 6, 1, left 6, up 1. That's the end of vector V. Then visually, if we were to take U and put it and start it from the end of V, we would land here. Also, if we take vector V and let it run from the end of U, you're going to land at the same spot, creating a parallelogram. For scalar multiplication, length and direction of the vector are affected. For example, if we let U be the vector 3, negative 1, write 3 down 1. Here's vector U. 2U would be the same direction, but twice as long. 2 times the length of vector U. If you have a negative, it will take that vector and run the opposite direction. If it's also scaled, it will tell you how much to scale it by. Negative 2/3 visually is going the opposite direction, but only having 2/3 of the length. Okay, so that's the visual component. Of course, you can just manually multiply 2 times U, 6, negative 2 when they're doubled. Negative 2/3 times U, negative 2/3 times 3 is negative 2. Negative 2/3 times negative 1 is a positive 2/3. So that's where your scalar multiplication comes in. Again, negating is opposite direction. Scalar is affecting the length. And then you just compare it to your base model U. If you've got a lot of vectors, given vectors V1 through VP, all of them in Rn, and scalars C1 through CP, then when you match them up, C1 and V1, C2 and V2, you've got a vector that's called a linear combination of the original vectors with those weights. The weights can be different, but they are matched up. C1, V1, C2, V2, and so forth. For example, let's let vector A be 1, negative 2, and 5. A2 is going to be 2, 5, and 6. And B, 7, 4, negative 3. Let's determine whether B can be written as a linear combination of A1 and A2. So basically, we're going to look for weights C1 and C2, where if we multiply these vectors by some constant, add them up, can we get vector B as an answer? Well, let's check it. C1A1 plus C2A2 has to equal B. Let's see if it has a solution. All right, so I'm just going to put them in here. Weight 1, vector 1. Weight 2, vector 2 equals vector B. Let's set these columns up in an augmented matrix and solve it. Now, see how many times it takes to row reduce to get all the way to the answer at the bottom? This would be definitely a case where you would put this into your calculator as a 3x3 matrix and select row reduced echelon form. If you do that, then instead of taking all these steps to snake through and get down to here, this is your row reduced form. Now remember, there were only 2 vectors in the beginning, so we had 2 weights. Weight 2, or C2, is equal to 2. Now we don't have to worry about this row because it's all zeros. So C2 equals 2. C1 plus 2C2 has to equal 7. C1 plus 4, after you've made the substitution, has to equal 7. So that tells us weight 1 has to be 3. Well, that also means that B is a linear combination of A1 and A2. excuse me for the background noise. So yes, B can be written as a linear combination of vectors A1 and A2 because we were able to find specific C1 and C2 weights to make it all work out nicely. Alright, so if you've got a list of vectors or a set of vectors in Rn, then the set of all linear combinations of V1, Vp, denoted by span of vector 1 through vector p, and is called the subset of Rn spanned by those vectors. Now, I know that's a lot to take in. Now, kind of the way to think of something visual with these spans is, let's take R2 for example. If you were to lay down a sheet of paper on your desktop and you draw two lines that don't lay on top of one another, then those vectors will span R2 because they will cover that two-dimensional space. R3 would think of it as a box or a cube or the room that you're sitting in. If you've got a set of vectors that will cover all that space, then that's called your span. Okay, so the span of V1 through Vp is the collection of all vectors that can be written in the form C1V1 through CPVP. Again, C is the weight, V is the vector. I just chose to write these as A instead of V. You can absolutely recall these V1, V2. All right, so we're going to move it up to 3 entries instead of 2. Let A1 be vector 1, negative 2, 3. A2 is 5, negative 13, negative 3. And vector B is negative 3, 8, and 1. This is pretty much a replay of the example we just finished. The span of A1 and A2 is a plane through the origin in R3. Okay, is B in that plane? Okay, now to give you a visual here, let's go back to that sheet of paper and a box analogy. If you were to take a box and put that sheet of paper in it, the sheet of paper is two-dimensional and the box is 3. So what we want to know is B on that sheet of paper. Okay, so I'm going to take this back out. Basically what you do is you always take your vectors. We're going to take A1 and A2. We're going to make that the first 2 columns in the augmented matrix. Vector B that we're trying to determine if it's in that plane, that's going to be your 3rd column. You can either RREF on your graphing calculator, or you can take the time and do the steps. Either way, we have the bottom left triangle of zeros. That's what you always want to go for. Now this has that form 0, 0, and a non-zero, so this is inconsistent. Remember, C1, C2, if everything is 0 up to the last column, and that's not 0, it's inconsistent. Any system that's inconsistent, that vector is not in the span of A1, A2. So this vector would not let on that red sheet of paper that I put in that little pretend blue box. This vector is not on it. Okay. And then one more example. Vector A1 is 1, 4, negative 2. Vector A2 is negative 2, negative 3, and 7. And vector B is 4, 1, H. Now we're going to leave one of these as a variable just to emphasize some of the types of problems we're going after. For what values of H is B in the plane spanned by A1 and A2? Okay, so same technique. We're going to create an augmented matrix with A1, A2, and B right here. If you wanted to try to row reduce, great, but this is one of those cases where since you have an open variable you're solving for, you're going to really need to just manually force solve it, just brute force. All right, so we're going to create 0 here, then and then finally here. That's the order you want your triangle of zeros. Here, here, and finally there. Negative 4 plus 4 is 0. Negative 2 times negative 4 plus negative 3. Again, we're following these sets of instructions or operations. Negative 4 times negative 2 is 8. Minus 3 is 5. Negative 4 times 4 plus 1 is negative 15. Now we're going to shoot for a 0 here. We've got that one. We want this one. 2 times row 1 plus row 3. Answer goes in row 3. So here, and the answer will go in row 3. 2 times row 1. So we have 2 times 1 minus 2. That's 0. 2 times negative 2 plus 7. That's 3. 2 times 4 plus H. That's 8 plus H. Also, row 2 happens to be all multiples of 5. So I'm going to do 1/5 of row 2, and that'll be here. 1/5 times 5. 1/5 times negative 15. Now, all we have left is to create a 0 here. Negative 3 plus 3 will make that happen. So we're going to do negative 3 times row 2 plus row 3, and we're going to force a 0 in that last little position. Negative 3 times 1 plus 3 is 0. Negative 3 times negative 3 is 9, plus 8 plus H, that's 17 plus H. Now remember, you don't want all zeros and something non-zero, otherwise it's inconsistent. There's only 2 weights that we're after because we're only given these 2 variables. So if everything is 0 until the last column, that also has to be 0. To be consistent, 17 plus H must equal 0, therefore H has to be negative 17. Give a geometric description of the span of V1 and V2 for vector 1 and vector 2. Notice that each entry in V2 is twice the amount of the entry in V1. Since V2 is twice V1, V2 falls on the same vector. Therefore, the span, if you ever see 3 dots lined up like that, that just means therefore. Therefore, the span of these 2 vectors is the set of points on the line that goes through V1 and the origin. Think of it this way. I can't draw a 3-dimensional shape on here, but if you were to, let's see, I'm just going to draw over the top and then erase it. But if you were to go through the origin, V would be a vector, let's see, 4, 5, negative 3. Again, I can't draw it 3-dimensional very well on here, but V2, because it's a scaled multiple of 2 from V1, it would go the exact same direction and just be twice as long. But they would be on the same line through the origin. Your e-text, and I highly recommend that you spend time reading the textbook for this class, gives much better visuals than I can on here. It gives you a lot better geometric visuals and explanations.